Should we have now?
To be honest, in real, although at the bottom, like by the time we get
Okay, cool. Just drop the money in and yes. Awesome. Next person. All right. So. Yep. Your name down already, right? I remember you.
Yeah, it could be a little bit $5.
Actually, just
Yeah.
it's perfect so that I know that. Right, how many want to have just
I'm looking at my this
Sorry? So
There is one on
wait,
Facebook.
okay, it's okay. Yeah.
Oh,
I really just had it.
hang on, let me check.
This is right. Yes. $2. Perfect. I need the menu. Okay, let me just check the number. Oh, harsh. Okay. You want money back?
Hello, can you hear me? I like. Sound good.
Okay.
Yes.
Hello, hello.
Yeah, you might. You might just want to log in using this.
Wait,
That was speaking from so far. Yeah, it's like how
You might want to ask. Oh, okay. Max because he is the boss.
Okay, sure.
you see speak from like Anzo's place.
yeah. Any issues?
Wait, is it? Yeah, is it that the sound that the voice is not clear enough? If I say this.
Voice is clear. Is that the voice and sound
Also, there's like a delay.
Oh, okay.
I see.
Okay, so whoever's on stream, we're a bit out of sync, but sorry about that. We'll get better next time.
Sorry. Oh, okay, sure. Yeah, I think they're still grabbing. So
Yeah. I know, it's okay. Like I'm glad it's not broken or anything. It's just a matter of pressing the button. I was scared. I thought everything was looking cool. And I just suddenly. Oh. All right. Okay, we wait for the last few people to get pizza and we will resume.
yeah.
Yes. Let me just give you the link.
I think you're getting Skype wrong. Guys, next time could you kind of RSVP? I think like the pizza we kind of ran out of them, so next time we could bring more food for you guys. So just RSVP next time. On Facebook, yeah.
You guys don't get any?
But you guys don't get any.
No. Alright, something else will be wrong on the link, but thanks for spotting out.
Thank you.
Alright, I think we got everything in order.
Yeah. So I'll resume the presentation.
Alright, everyone, so we're continuing. So Anzo Sensei, please take it away.
Yeah. Okay. So we talk about like how you can add up two vectors provided they are of the same length, and also how you can multiply a vector with a scalar. So the same thing happens to a matrix as well. So as long as they are of the same dimension, you can add them up, as we might see later. So just now we talk about like what is a matrix, which is like a more generalized vector. So recall that we have this matrix just now. So A equals to, like for example, you can treat it as like what order like an order collection of vectors. So you can split it into 2 minus 4, 8, 3, 1, and 2, or just do any concatenation as you like. But then there's also another more important thing that is called the scale. What is that called? What is that called again? Okay, so it's called the linear transformation of vectors. So so what exactly what linear transformation mean we'll see later. But before that, let me talk about what a dot product means. So dot product just simply means so as you can see just now, we can add two vectors together. But then does it make sense to multiply two vectors together? That's a way which we'll see as a dot product. So again, they must have the same dimension. So let's just say that we have a random vector. So v equals to 1, 2, 3, and 4. W equals to like 5, 6, 7, and 8. The dot product is simply the sum of 1 times 5 and plus 2 times 6 plus 3 times 7 plus 4 times 8. So what is this turned out to be 70 if I do my math correctly. So here we can say that v dot w equals to 70. There's also another thing called cross product, which we don't really cover right now. And exactly why do we need dot product? Is because we have this thing called matrix multiplication. So matrix multiplication, it will be very mind-blowing for you guys right now if you didn't know any linear algebra beforehand. So don't worry, you guys will get better and better in this when you have more exposure, especially when you take the classes. So matrix multiplication. So first of all, we talk about like how we can add two vectors or two matrices if they have the same dimension. Unfortunately, matrix multiplication doesn't exactly work this way. So, so before that, let's talk about what's the dimension of the matrix look like. So, so we call this matrix 2, 3, minus 4, 1, 8, 2, minus 2. Does anyone know what's the dimension of this one? Yeah. Yes. So it's 3 by 2. So this is a 3 by 2 matrix. Why do we say so? It has three rows and 2 columns. So it's a 3 by 2 matrix. So we can So we can multiply two matrices. Let's say one is A times B, the other is C times D. So when are we allowed to do matrix multiplication of A times B and C times D? Does anyone knows the
B
condition?
and C are equal.
Yes, B must be equal to C, which means that here's another mind-blowing thing for you guys. Even though we can do, if B equals to C, let's say it's A times B and then B times D. So we can do, let's say this one is A, this one is B. So we can do multiplication of AD, but BA is not defined if A is not equal to D. So for example, we have this, let's keep things a bit simpler. So let's say we have like D equals to 1, like let's say 2, 1 and 1, 2, 3. So let's say A. So A times B is defined, but B times A, okay, I shouldn't really use this dot product symbol. It's very confusing. It's not defined. And even though they might be, they are defined, like let's say you have like 2, 1 and 4, 5. Sure, AD and BA are defined, but they are not necessarily the same. So here's one thing about matrix is that you have to be very particular about the order. It's not like 5 times 7 equals to 7 times 5. It's you'll see this when you see more example. And exactly how we do the matrix multiplications is like you do the dot product of the row of the first matrix and the column of the second matrix. So so it's kind of self-explanatory over here, but I'll just demonstrate it. And please tell me if the things I write on whiteboard is not clear. I can pause to explain a bit more. So let's see this one. 7, 8, 9, 10, 11, 12. So before that, let's do some warm-up exercise. Does anyone want to share like why are we allowed to do matrix multiplication like this? Why is this multiplication defined? Yeah.
There's a 2 by 3 into 3 by 2.
Yes. So the 2 by 3 and 3 by 2, the middle dimensions are the same. And the other thing is that if you have 2 by 3 and 3 by 2, if you multiply this together, you'll get 2 by 2. This 2 comes from here, this 2 comes from here. So knowing this, let's fill the blank. The first one is, so this is the first column and the first row, first column. You take the dot product of the first row here and the first column here. So in this case, we have 1 times 7, 2 times 9, 3 times 11. As you can see from here, this adds up to 58. And how about this one? This one is the first. This one is the first row and second column. So we take dot product of first row and the second column. So 1 times 1, 2, 3 dot 8, 10, 12 equals to 8 plus 20 plus 36, 64. Yeah, should be correct. So this one, the second row and first column, 4, 5, 6 times 7, 9, 11, 28 plus 34. Yeah, I wish I have a calculator, but whatever. And finally, the last one, second row, second column, second row, and second column, 4, 5, 6, 8, 10, and 12. 32 plus 50 plus 72 equals 154. So this is the final matrix you should get. If you couldn't really follow, I encourage you guys to like after you go home, you can try to work this out yourself. So you can see that so you can see that when you multiply two matrices, you get something like this one. But then just now I talked about linear transformation, and then it obviously didn't become obvious why are we talking about this right now. So imagine that you have a simplified form where this one is not a matrix, but just a vector. So it is something like this. For example, you have this one and you don't have this one. Then all you have left is just this one. So in other words, let me just tell you that 1, 2, 3, 4, 5, 6, 7, 9, 11 equals to 58, 139. So in other words, right, you if let's say V is a vector, A is a matrix, and we want to define like a transformation T of V equals to A times V, then you'll get things like T of 7, 9, 11 equals to 58, 139. So basically, you can think of it as a function, a linear function that satisfies the property that. And is that a way to? Yeah, got it. Okay, so there are two things that that defines the linear function. One is that f of u plus v equals to f of u plus f of v, and the other one so it's like you can split the plus out or combine them, and at the same time if it's what scalar multiplication, you can also take the c out or put it in. It shouldn't affect your result. So this is also one very important thing about linear algebra, as we might see later. Yeah, this is one. So this is one illustration about what a linear transformation means. And yeah, okay, this looks very abstract. So let me explain again. So just now we talk about A equals being equal to 1, 2, 3, 4, 5, 6, which is so n equals to 2, n equals to 3, because this is the because this is the dimension. So it takes, in this case, it takes ax equals to y. So this one, x is have the form of 7, 9, 11. So the length is equal to 3. The final output we have is 58, 39, 139, which has only 2 elements. So the length is equal to 2. So essentially, we are the transformation of A brings the vectors of length 3 into to a vector of length 2. So just think about it this way. Any questions to this point? Okay, I'll go. So yeah, another thing is called the inverse of a matrix. So what does an inverse exactly mean? So so first of all, this is only defined on matrices that are square. So anyone knows what is a square matrix? Yeah. So basically, the number of rows is the same as the number of columns. So is this a square matrix? No. So one example of a square matrix is, let's say you have 1, 2, and 3 and 4. But even though something like this A is a square matrix, an inverse doesn't necessarily exist. And so exactly what qualifies as an inverse? So the inverse must satisfy that, let's say A minus 1 exists, right? Then it must satisfy that A minus negative 1A, it equals A negative 1. So basically, this is a 2 times 2 matrix, 2 times 2, or in general, like more generally, n times n must be equal to I. So what does I actually mean? This is called the identity matrix. Given in the form of 1, 1, 1. So all the on-diagonal entries are 1, and the others are all 0. So in this case, I 2 times 2 is the same as 1, 0, 0, 1. Yeah. Anyone wants to take a guess on like why is an identity matrix useful? Anyone? Yeah. So we can show that if you multiply an identity matrix of n times n with a vector of length n, this thing will always return V. Yeah. And finally, okay, not finally yet. So this is one very important point about what we have taught just now, meaning solving linear systems of linear equations. So anyone still remember what is the linear system of linear equation that I showed you just now? It is just the same. It is the one that I talked about in the very beginning. So like x plus y plus z equals to 2, 2x minus y plus 4z equal to 1, and the other one, yeah. And then this is the tool for you guys to solve it. So the thing is that if so the thing is that you want to model them as a of matrix and vector. So in the case just now, right, all the coefficients 2x, like what x plus y plus z, the coefficients 1, 1, 1, and the others you arrange them into a matrix A, and the thing that you want to solve, you arrange them into the vectors x and b. X are the variables, b are the numbers. Then you will find that x equals to A inverse of b. So there's a more concrete example over here. So recall that what we want to solve just now. Okay. So anyone remember this equation? Yeah, this is just repeats what I showed just now, like in the beginning. So these are all the coefficients: 1, 1, 1, 2 minus 1, plus 4, and then 3, 2 minus 3. So we will just put A in the exact form: 1, 1, 1, 2 minus 1, 4, and then 3 minus 3. And then this will just be x, y, and z. And we want to make sure that this adds up to 5 and 7. Exactly why is it so why this will imply this one? This is your exercise. Just verify that if you multiply this, you'll get x plus y plus z, 2x minus y plus 4z, 3x plus 2y minus 3z. Yeah. And then you want to make sure that this is the same as this one. So the good news is that this A turned out to be something that is invertible, meaning that A inverse actually exists, and you can finding an inverse is actually something something computationally heavy. But then in this case, it's not. I cheated by using Python to do like A's inverse for you for me. But if it's 2 times 2, then it's way more straightforward. I'll leave you guys to explore the ways. So it just turned out that A inverse equals to has this form, and in order to recover x, y, this one x, y, z, you just do A inverse times B, and you get the answer. Here I'm just there's another way to solve this one that is called Gaussian elimination. It's a bit longer process than this one. If you don't have a computer in front of you and you have to do it by hand, so this might be one other way to do. Yeah, I'll just write the name down. Gaussian elimination method. So yeah, I'll leave you guys to explore this yourself. And there's one other thing called the transpose. So it's basically just you treat row as column and column as row, This might look something that is very small, but then the application will come out later. And the transpose of a matrix product, yeah, A times B, the whole thing transpose equals to B transpose times A transpose, yeah. Here are some of the spatial matrices. So diagonal matrix is like the identity. It is a broader set from the identity matrix itself, except that for identity matrix, for diagonal matrix, the only non-zero allowed entries are on the diagonal. The things that are off diagonal must be zero. It's just that for identity matrix, it must be a square, and all this has to be 1. So orthogonal matrix is where A transpose equals to A transpose times A equals to the identity matrix. This one will show up later. Don't worry if it doesn't make sense to you guys. And symmetric matrices means A equals to A transpose. So one thing about symmetric matrix is that it says A equals to A transpose, right? So what does it exactly mean? It just means that the off diagonal matrix the off diagonal entries are similar. So from here you can know that A must be a square. So exactly what it means then is that, let's say you have this one as the diagonal entries we don't really care, like 1, 2, and 3. This one must match this one. So if you have like -5, this one must be -5. If let's say this one is pi plus 2, this one must also be pi plus 2. So if let's say this one is square root e plus 5, what's the value of this one? Does anyone, like, given that this is a symmetric matrix, what is the value of this one? Yes, it should be square root e plus 5. Okay. So, ta-da! So identity matrix is what we say. I talked to you guys just now. Basically, if you multiply identity matrix with any suitable length vector, you'll get the vector itself. Zero matrix is where you have all entries equal to 0. So it just means 0, 0, 0, 0, 0, 0. So one example, one application is that, let's say this is a zero matrix, and suppose you want to multiply this one with -5 and then pi plus e plus pi, and then the other one is, let's say you have e to the power of pi plus 6. What should this return? Yes, it should return 0. So the moral of the story is that if you multiply a zero matrix with anything, it should return 0. If you multiply any vector with a 0 vector, it should also return 0. If both these are non-zero, can it return 0? The answer is yes. This is called a singular matrix, which I didn't really explain properly just now, but yeah, you might see it more later. So another thing is the concept of eigenvectors and eigenvalues. It just means that sometimes it will be useful to have things like AB equals to lambda V, where this is a constant. So like using a very dumb example we have just now, like 1, 1, 0, 0. This is an identity matrix, and let's say you multiply by 2, 3, you'll get 2, 3. And this is in fact the same as 1 times 2, 3. And then of course there are like more there are like more things happening here. One good thing about fully diagonalizable matrix, this is just like a very special set of matrix, because not all matrix fall into this set. Let's say A is fully diagonalizable, then you can write it in the form of like P diagonal P minus 1, where P is the matrix containing the eigenvectors. And if you go back to the example that I might have just now, so let's say P equals to yeah, I don't want to waste too much time to recover the thing just the eigendecomposition of this one, like writing it in finding the eigenvectors. So let's say you have p equals to, let's say you happen to be able to write a equals to p minus 1, and let's say p is the form has a form of 1 1 1, 2 minus 1 4 3 minus 2 3, and it just turned out that p of p inverse is the same as this one. And let's say, and then B has to be a diagonal matrix, meaning that 0 0 0 0. If it turns out that this thing is 1 2 and 3, then what the good news is that you can find the power of n like a high power of a very quickly. So let's say you want to find a power 100. So it just means a times a like 100 times. If you just do it like by hand or by computer, you'll realize that this is a very slow process when a is like, let's say a is not as small as this one, but it has like 1,000 times 1,000 dimension, then this will take a lot of time. But if you manage to write a into this form, then you notice that a to the power of 100 is the same as p to the power of p times d to the power of 100. So so you just basically just and then finding the power of a diagonal matrix is easy. You just have to multiply each diagonal. You just have to raise the power of each diagonal entries. So yeah, not all of them are fully diagonalizable. Like for example, this one is not fully diagonalizable, and then it cannot be written into this form. So yeah, this is a meme that I posted on Discord back like a few days ago. Anyone knows what it means exactly? This one. Yeah, this is an identity matrix. It's like if you multiply it with any vector, you get the same vector. This is the zero matrix. It just returns 0 all the time. Minus delta, small perturbation, almost 0. This is an interesting one. So this one, if you see something like for higher dimension, it's trickier. But if you see 2 times 2 in the form of like cos theta, and then this one sine, negative sign, and sine, it basically represents a rotation of theta degree. This one, as you can see just now over here, is not fully diagonalizable. And this one is not invertible. The inverse doesn't exist. So basically, this thing is not defined. Okay, here's something a bit more fun applications to machine learning. Probably the reason we are here. So first of all, let's talk about the norm of something. So norm is, you can think of it as length. So recall that we have the Pythagoras theorem on saying that, right? If you have, so let's say this is the origin. This one is 1 1. So what should the length of this vector be? Sorry? Yeah, so this one should be square root 2. It just turned out that in pure math, there are a lot of ways of defining the length as long as it follows certain inequalities. So for example, the length of each vector must be greater than 0. And if and only if x is a 0 vector. So this is the first one. The second one is a triangle inequality. The length of x plus y, like treating it as a scale vector multiplication. must be less than the length of x plus the length of y. Which makes sense because, like, if you take a triangle, the length of this one must satisfy z must satisfy less than or equal to x plus 1. And then finally, if you multiply by a constant, the length must be multiplied by a constant as well. So here's this is a bit more abstract as you can see from here, but then it just means like there are a lot of ways to take the norm. For this one is the p norm. What we talked about just now is the so-called L2 norm, where because we just take the square root of the sum of square of the coordinates. So it just means that, like, if you have a vector at like 2, 3, 4, the length is essentially 2 square plus 3 square plus 4 square. Take the square root and you'll get the square root of 29. And it has a few uses, as you can see over here. The matrix norm, we can define the matrix norm as well. Like, if you like, you can define a way where it's simply just taking all the sum of squares of all the entries, and then you take the square root. But sometimes it has a different meaning. So for this one, we are more interested in, like, if we multiply, let's say you have a vector x non-zero. If you multiply a by this vector, how much will the norm grow? So yeah, eigendecomposition, we have shown this just now. There's one very beautiful thing about eigendecomposition. So I showed you just now that not all the matrices are fully diagonalizable, but there's a very special class of matrices that are fully diagonalizable. That is when it is symmetric. And what's more interesting is that we recall that just now I talked about A in terms of P, D, P inverse. So if this one is symmetric, it will follow that. Okay, let me just write it in the nicer form. If this one is symmetric, this one you can find P and P inverse such that this one is an orthogonal matrix, which means that P inverse equals to P transpose, or P transpose equals to P transpose times P equals to the identity. Yeah. And this is just an illustration on, like, if you take all the vectors of length 1, how would it look like when you multiply it? So this is just like a locus. So these are just these are just facts from eigenvalues, meaning that if a matrix has inverse if and only if all the eigenvalues are non-zero, it means that if it has a zero eigenvalue, meaning it means that you cannot find the inverse. And then if any two eigenvectors share the same, and then this one also this one simply means that, right? Let's say the second one is also very useful fact, and sometimes it kind of confuses people as well. Let's say you have x and y that are, like, very different from each other, meaning that they are not scalar multiples of each other, vectors and vectors. Let's say you also have a x equals to lambda x, a y equals to lambda y. For the same lambda, then if you take the linear combination of x and y, meaning an a x plus b y, where this one is scalar, this one is scalar, then you also get ax plus by. So let's say this one is z equals to lambda ax plus by equals to lambda z. So anything in the span of x plus y is also an eigenvector of A. So yeah, So this is something that you might only see in your second the second linear algebra course. Make sure I highly encourage you guys to take that course. It's not mandatory, but it's very useful and very cool. So this is another way to factorize matrices. So recall just now that I talked about how some of the matrices are not fully diagonalizable, and even if it is not guaranteed that the eigenvectors are all are orthonormal to each other. Like think of it in an n-dimensional space where you want something to be perpendicular to each other, but they are not. It's not the case, and then worse still, what if your matrix is not square matrix? All the diagonalization just doesn't make sense anymore. So this is another way to factorize matrices. It means that you can see from here, every matrix has a singular value decomposition. So this one this is a diagonal matrix. This one U and V are both orthonormal. So yeah, this is how you might want to visualize it yourself. So another fact is that if you consider the let's say you have a matrix A, n times n, a to the t times a. Does anyone know? Okay, a to the t means A transpose. Does anyone know what is the dimension of this?
Is it a square matrix? Sorry, n times n.
M times, okay, A is not a square matrix. How about this one?
M times n same.
Yes, this one, this is n times n. So this one, you take a transpose, it should be n times m. So yeah, it will be an n times n matrix. And the best thing is that it's symmetric, which means that you can basically take you can basically diagonalize it and then all the eigenvectors will be orthogonal to each other. One other cool thing is that all the lambdas, if A transpose A equals to lambda x equals to lambda x, we are guaranteed that this lambda is greater or equal to 0. And then we also know we have this cool fact called A equals to U diagonal V transpose. It turned out that right, and then this one, let's say this one is and this one is a diagonal matrix of this one, all the values over here, and then this are all 0. It turned out that these ones are the square roots of all the lambdas, all the eigenvalues when you take of this A transpose A. So this is one cool. You'll see the application later. So covariance matrix is just okay. It's just one example. This covariance things might come out in the stats workshop later. Yeah, so I don't explain too much from here. So principal component analysis. This is kind of like the holy grail of the workshop from today. So sometimes you wonder, right? You took a photo and then the photo is too big, and then you use like an app to to reduce the dimension. So exactly how do they reduce the dimension while still preserving the beauty of or the clearness of your photo? So this is one application from here. It just analyze your photo and then take the few more significant components, so to say. We'll see the application later. So this one is something that this one is an illustration. Exactly what it means is that, so for example, you have this 2D. So imagine this as like a 2D surface, right? And then you have all the points scattered around over here. Imagine you take the best straight line, and then this one you take the 90-degree projection from here to here, here, and then you approximate the whole diagram in this form. So this is the dimensionally reduction that that reduce your dimension into like reduce your whole like your whole diagram into just one dimension, while still preserving each point as much as possible. So this one is also the same thing when you have like a 3D data, and then you want to find the plane, the 2D object that such that everything can be approximated on that plane, and still doesn't lose too much of the information. So the way of doing this, I think we are kind of running out of time, so I'll just briefly go through it. In math, it means that you want to you found the sorry, how should I say this? So let's say you did the singular value decomposition, and then you find the let's say you have you want just like the dimension equals to 3, so you just take the three highest singular value, and then take this, and this will be your principal component. In a more concrete meaning, the math behind it. So we break every vector. So the vector the vector simply has when I say n over here, it just means the n dimension, but there might be like way more than n vectors, and then we only want we only want like k of them. Sorry, k of the dimensions. So we just approximate it from using like one constant and k of the most significant components, and discard the rest. So this is something that I saw from Andrew's video. I took this online course before. So on average, right, it's enough just to retain like 17% of the dimensions, and your the quality of your image, for example, will be retained by 99%. So you can see over here what of each of the principal component might look like, and the dimension reduction. The dimension reduction app just take whichever that is the closest to your face. Linear regression, I'll just gloss through over it. It is part of the stats workshop as well, but then I talk about this because you can use linear algebra to solve this. So yeah, so it's like let's say you have it can be generalized for higher dimension as well, but let's say you have just xi and yi. You want to find the line that fits these points the best. So yeah, this is the line of best fit. And why do we care about this? It can be used to make a prediction. So let's say we know that at this temperature, 30 degrees, it's like breeding season. There are a lot of geese on campus. When it's -15, all the geese flew to the south, and you only have 10. So let's say it's 5 degrees now. How many geese do you predict it to have on campus? Of course, this is a very lousy model because the number of geese cannot go negative. But yeah, this one just for your information. Yeah, I think I'm done with this. Thanks for your attendance.
All right, so thank you, Anzo Sensei, for coming and teach us everything. All right, okay, so everyone, so next up we're gonna have a statistics workshop covered by our very own Frieda right here. But first, let's just have a quick break. So during this break, I want your help. So I posted a link on Discord asking for anyone who showed up today to do a quick sign-in. This is very important for us because we need to know how many people came so that we can get pizza and like other wonderful food for you next time. And also, thank you for the 4 people who already filled it out before I even asked for it live. So yeah, the rest of you just fill out as well. Because remember, if I remember who you are, next time you show up, I'm gonna be like, hey, I know you. Get food now, right? So yeah. So let's do that. And if anyone doesn't have the link, let me know so I can just put it on the whiteboard. I guess everyone has the link, right? All right, cool. I'll put it on the whiteboard here.
Is it? I have it in the chat for a while.
You sent it? It's fine. Mine was the one which had the this as well as this. It didn't have the there was no laptop with both USB and HDMI. Or okay, so I'll just go to Messenger.
Okay, so it could be quite a hefty link. I don't know why it was made like this. So yeah, I made it as big as possible. You don't see it just like come up. It's okay. Yeah. The personal information is very important to us. Cool. So how's it going?
Oh, sorry. This I was doing this this end. I can't.
Or you guys tried to do
What? Well,
Please double check if it is still live. So make sure it's live.
yeah.
Okay.
Not quite sure how to change the resolution for it.
possible to move it back again?
Sure.
Move it back.
Oh, sorry.
Yeah, move the table forward. Yeah, move the table forward. Okay. Pick it up. I think it's a lot better now. Let me check if the live stream is still working.
I think it's okay. Do you have anything in that margin?
Not too much. Are you good? Okay. All right, so we'll be starting the statistics workshop right now. Right? All right, we're good. Okay, so I just want to say thank you everyone for coming out after a long day of lectures. You guys are still here for another lecture. I know there's a geography food, but even then, I'm really happy that you guys have stuck with us. This second workshop or the second talk will be a little less math heavy. So hopefully you still have the stamina for that. I'll be talking about another one of the foundations for machine learning and data science, which is statistics. To be very straightforward with you, I actually haven't taken any statistics courses beyond the bare minimum required for a computer science course. And although I've done machine learning internships, I haven't specifically done things directly involving statistics. But statistics is core to data science as well as to some topics within machine learning. Machine learning is closely associated with statistical topics such as statistical modeling, as well as optimization in machine learning, as well as being its own subfield. So that's where the ties come in. And then also touch upon the statistics concepts foundational to or core to data science as well. So there's a lot to cover, but I'm hopefully going to highlight things that are important to data science and machine learning, not necessarily try to cover every comprehensive topic that you would cover in a standard statistics major. So first off, what is statistics? There's a lot of different subfields within it. There's descriptive statistics, where we're given a fixed data set and we want to be able to find some meaningful summary of the overall data set, such as the mean of the data set or the variance or the skewness of it, maybe the max, min, ranges, or the other quantiles. There's also statistical inference, which is the very important task of inferring the general parameters of the larger population based on a sample from the population. So based on a sample data set, we have some unknown parameters, and we want to estimate those. There's statistical modeling, which is a core concept where we use mathematical models to describe a family of distributions. And we want to learn, and we want to reflect what are, or infer what parameters reflect our data generating process. So here we're making some assumptions on our data generating process. Maybe we assume it's Gaussian or something. And then that would be a class of probability distributions, which we're using. There's also non-parametric statistics, which you might encounter a little less of, but there's non-parametric statistics for both statistical inference and descriptive statistics. To give you a concrete example, using a histogram to describe your data set is a non-parametric way of example of descriptive statistics, because it doesn't have anything to do with the parameters of any distribution. It doesn't make any assumptions on what the distribution precisely is. Other examples include kernel density estimation, as well as k-nearest neighbors, if any of you have heard of it. So non-parametric statistics, loosely speaking, you can think of it, if your method increases in complexity or depends on the size of the data set, then loosely speaking, this would be non-parametric statistics. There's also experimental design. So if you're looking to conduct a survey, making sure that you're obtaining an unbiased data set, you're not introducing any undesired biases, making sure, say, you have a properly set up randomized control trials or using stratified sampling. This is its own subject earlier on in the data collection process. And then there's, underlying all of this, there's a concept of probabilities and knowing the important distributions, knowing the mathematics, how to work with all of this. So those are the topics that you might see covered in a curriculum, but where this comes into play for data science, I just threw a bunch of phrases up here, but on the right here, you can see a diagram of the data scientist's workflow. So first, say they import a data set, then there comes the very important stage of tidying that data set, so data cleaning. And then you have this loop of transforming your data, visualizing your data, so exploring around, trying to understand, look for patterns within your data set, and trying to model it. And finally, the final stage is communicating whatever insights you have to whoever uses that information. For example, if you're working in a company and you're working with product managers, then you want to be able to both handle the business side of communicating those insights, as well as the analytical side of being able to interpret and analyze your data and fit a model to it. So on the left here, I gave the example of A/B testing. Say you're Facebook and you want to introduce a new feature to Messenger, for example. How would you properly conduct an A/B test? Would you do it based on location so that people's friends probably all see the same, are all in the same test or something? There's also other concepts that you would encounter when it comes to practically employing or practically implementing data science. There's missing data imputation. Say your data set is missing a lot of values. How do you deal with that? Do you just replace them? Do you delete things? Do you try to model it if you can make some assumptions on it? There's model selection, where you're trying to select the right model that is not too complex, that it overfits your data, while still being able to properly model your data. There's the whole business of interpretation, properly applying what you determine from statistical tests, say like hypothesis tests, to derive valid conclusions on your data, and then employing those insights. And then there's the question of prediction. Like maybe you're a retail store and you want to predict sales for a certain item in your inventory. So all these things come together in practice. So I'll give you an overview of what I'll talk about. First, I'll start with the basics, because we need to at least be somewhat familiar with probability. Maybe you've seen this in high school classes, but I'll still try to run through it. Maybe there'll be things that you haven't encountered before. Then we'll talk about something that you probably haven't maybe heard before, the divide between frequentist and Bayesian statistics. After that, we'll touch on hypothesis testing, followed by statistical inference and statistical modeling. So linear regression, which Anzo touched on in his presentation, as well as logistic regression. These are both foundational statistical modeling methods in both machine learning and data science. So probability. First off, when we talk about probability, we have some random variable, say the outcome of a dice roll, or maybe what the temperature is like, whether it's going to rain or not tomorrow. There's some uncertainty associated with this variable, and it's going to take on some outcome with some probability between 0 and 1. And your random variable can be discrete or categorical. In special cases, it can be binary in the case of a coin flip, or it can be continuous, say with the temperature example. And then associated with these, with the random variable, you have the probability mass function if it's discrete, or the probability, the density function if it's continuous. And as well, you have the cumulative distribution function, which is just if you sum up all of the probabilities less than a certain value, that's what that would look like. And then using the cumulative distribution function, I mean, one reason why we're interested in that is that we can reparameterize our probability, a random variable, and derive the reparameterized probability mass function, or PDF, by differentiating the cumulative distribution function. So one essential concept in probability is taking the expectation of a random variable. You're probably familiar with the mean of a random variable. This is maybe like the university level concept of that, where we're taking, it's essentially the mean in this case. So the expectation of some random variable x would be the mean. And the way you calculate that is that you weight the value of each of the possible, or you weight each of the possible outcomes with the probability that it occurs. So when you calculate the mean for, say, a data set of the heights of people, you probably just divide it by the total sample size, n or something. In this case, this is a slightly more general version where you have a not necessarily uniform distribution. So in that case, this is the more general form. And then for the continuous case, you would be summing over infinitesimal values dx. And then more generally, you can take expectations of some other random quantity. So some other expression, say the variance, is just the expectation of x minus its mean squared. And it can also be written in this way. Another thing is if you have two or more random variables, we're usually interested in knowing whether or not they're correlated with one another. So let's say you have x and y. Let's say x and y are both categorical random variables and they take on 3 different possibilities. We can draw the joint probability table. We have the joint probability distribution function where we consider what values each of those takes. So each of these cells within the table is f, where f is the probability distribution function, the joint function for x and y. And then if we marginalize, so if you look at the bottommost row and the rightmost column, the rightmost column is just the probability density function, or the probability mass function for x alone. And then the bottommost row is just the probability mass function for y alone. So summing along, or summing over a given random variable is called marginalizing out that random variable. And then here we all, when we talk about multiple random variables, we're interested in whether or not they're independent of each other, whether they're dependent of each other. We can also define the covariance matrix and pairwise correlations. So in this case, maybe some food for thought. Do you think x and y are independent of each other? So they're independent if and only if for all events A and B, then the probability of A intersect B is the same as the probability of A times the probability of B. So in this case, the two random variables are dependent on each other. So Anzo also touched on this, but you can define the covariance between two random variables. And this is just a generalization of the variance for two random variables, where it's very similar to the formula for the variance here. But now we have the expectation of x minus mu x times the expectation of y minus mu y. And one thing to note is that if x and y are independent, then the covariance is going to be 0. But the converse isn't necessarily true since we're taking the expectation over. And then similar to the covariance, the correlation quantifies how correlated or how related with this, how strong the statistical relationship is between two random variables. So this is just the covariance normalized by the standard deviations of x and y, and it always lies within the interval -1 and 1. So if the correlation is -1, then the two are perfectly negatively correlated, and then if the correlation is 1, then they're perfectly positively correlated. But one important thing to note as a responsible data scientist is that correlation does not imply causation. So you can't assume that, oh, just because you went to the statistics workshop and then you received a 95% on your statistics course, it wasn't necessary because of us. Or maybe it was. We don't know. And here's a fast fact, since you guys are all linear algebra experts now and you know about eigenvalues. Covariance matrices are exactly those matrices which are symmetric, so their transpose is equal to each other as you learn, and positive semi-definite, which is to say that all eigenvalues are non-negative. Okay, so next, a very important theorem when it comes to probability is Bayes' theorem. And this, you can see in the nice visualization on the right, says that, I guess I should define the notation first. The probability of A given B is equal to this expression on the right, which is the probability of B given A has the probability of A over the probability of B. Just a hands up, who's never seen conditional probabilities before? Okay, so in this notation, we have a bar in between, and that's saying we're conditioning on some event happening. So here, P of A given B means that we're assuming that B is already true. What's the probability in that case of A being true? And then you can derive this formula intuitively by just restricting yourself to those cases where B is true. So if we're interested in the probability of B, but we only care about the instances, if we're interested in the probability of A, but we only care about the instances where we already know B, the value of B, then we only look at those instances where the value of B is what we assume it to be given. So the top you can rewrite as P of A and B. So those are the cases where A takes on the given value and B takes on its given value. And then we divide over only the cases where P of B is true. So here's an example, and Bayes' theorem is really important to being able to correctly compute probabilities that might otherwise end up being unintuitive. So let's say a patient goes to see a doctor. There's a test that has 99% reliability, which means that if you're sick, then you'll test positive 99% of the time, which is correct. And if you're not sick, then you'll test negative 99% of the time. And we also know that only 1% of the people in the country are sick. So let's say the patient takes this test and the patient tests positive. What are the chances that the patient is sick? Who thinks that the answer is 99%? So either you're still thinking or you're guessing that it's wrong just because I said it's unintuitive. But in whatever case, you guys are all correct because it's not 99%. If you work through the math and apply Bayes' theorem correctly, then it turns out that the correct answer is 50%. So you can try calculating this for yourself. Next, we have some essential probability distributions. So there's the binomial distribution, which is a categorical, more specifically a binary distribution. So you can think of it as the class of probability distributions for a coin flip, where heads occurs with some probability p, and then you take n coin flips. What's the number of heads that you see? So with a fair coin flip, that would be bin of n 1/2, because heads occurs with probably 1/2. There's also the multinomial distribution. So for example, a dice roll, or you have a number of classes and they each have some probability. Then there's the continuous probability distribution, the normal distribution, which I'll talk about more later. And then there's the geometric distribution, which is the number of rolls before, let's say the number of coin flips before you see the first tail, for example. There's the Poisson distribution, which is also a discrete probability distribution, and it's the number of events that you see if each of those events is independent, if the time at which each of those events happens is independent over a given time interval. And then there's negative binomial, there's the exponential distributions, there's the gamma, which you might all see if you take stat 230 or stat 240. Then there's the student's t test and student's t and chi-square distributions, which you would run into if you're conducting hypothesis tests. So I'll talk more about the normal distribution because it's very important. And as I referenced on the previous slide but didn't mention, both the binomial distribution and the Poisson distribution have large-scale approximations using the normal, which is to say that if we're talking about a binomial distribution where n is very large, then we can approximate it roughly by using a normal distribution with the same mean and the same variance. So the normal distribution, one reason it's so important is because of the central limit theorem, which loosely speaking, under some conditions, if we take n IID random variables, so if we take n independent and identically distributed random variables that all follow the same distribution, and let's just for simplicity's sake say they all have zero mean and they have variance sigma squared, then if we compute the average of those n random variables, then this is itself a random variable, and that distribution of that random variable z approaches a normal distribution as we take n to infinity. So let's say you're measuring the heights of people. As you increase your sample set size and you compute the average, if you compute the average the average height of a person, then that is a random variable that approaches a normal distribution. Another interesting fact about the normal distribution is that it's a distribution with the maximum entropy for all real value distributions that have the same mean and variance. So the mean and the variance are derived based on the first two moments of a probability distribution. And the moments are just the expectation. The moments of a random variable are the expectation x to the k for some integer k, where x is your random variable. So what this is saying is really that when we say it has maximum entropy, it's like the same as saying we're making the least amount of assumptions on our probability distribution. So if we just want some garden variety distribution, it's best to take a normal. The entropy is like a concept from information theory, and it's closely tied to other concepts in probability, along with coding theory. But essentially, it's saying we're encoding the least amount of information, like the least amount of prior assumptions on our distribution. Another nice thing about the normal distribution is that it has rotational symmetry. So it's rotationally invariant if you think about a multivariate normal. So at the very top image, we see a normal distribution for a single variable, and you can see the little brackets below indicating the regions of falling within a single standard deviation, falling within 2 standard deviations, falling within 3 standard deviations. As you get more and more close to the edges, those are more statistically rare. The other two images, actually, we had an overlap in the two presentations, but the other two images show the PDF for a multivariate normal distribution, where you have two random variables, both following the same unit normal distribution. And then you can see it's rotationally invariant around the axis, and there's a nice way of thinking about geometrically. Okay, so now for the feature presentation, which is statistics. So what do we talk about when we talk about statistics? There are actually two different philosophical schools of thought about statistics. So there's a frequentist approach, which you're probably most familiar with, and here we think about the probability of an event as being the limiting value. It's the limit of the frequency that some event occurs as we take more and more samples. And then within frequentist statistics, we have the whole area of classical hypothesis testing, where we have some kind of hypothesis that we want to test. And then there are statistical approaches to being able to find out whether or not our sample data set is consistent with the hypothesis or not. But there's a whole different way of thinking about probabilities, and the two schools of thought each have their criticisms, and there's some controversies, and sometimes you might identify as a frequentist and then slowly be converted into a Bayesian. There's a whole history behind it. But Bayesian statistics is subjectively more subjective. It talks about the probability of an event as being based on our subjective belief in its likelihood of occurring, which is to say, the probability that some event occurs depends on how likely we think it is. So we start with some prior distribution, and then based on new samples, we update our prior to obtain a posterior distribution. So there's a little image in the bottom, but I've blown it up, I think, on the next slide. And here, this is where Bayes' theorem comes in. Here, theta is generally used in the literature in machine learning or in data science. Theta generally refers to the model parameters. So when we have a statistical model, usually if we're working with in the world of parametric statistics, then we have model parameters, data, and we want to fit them to the data. And then here, X is our data. And so here we would apply Bayes' theorem. P of theta is our initial prior, and then we see F, which is the likelihood of seeing the sample given our current model, given the model with the parameters that we have right now. And then we divide by the probability of X happening, although this is usually a constant. And then we obtain our posterior based on this. So we update our model parameters given that we've seen the sample X. So here's that image blown up a little more. We start with, let's say we're trying to fit a binomial model and we're working in the world of Bayesian statistics. And we start with, say, a fairly uniform prior. And then we draw samples. So our first sample is a failure. And here we're trying to estimate the parameter P. So in a binomial model, let's say we have a coin flip and we're trying to guess the probability that the coin will return heads. So the first time we see that it returns tails instead. So we update our prior and then we have in n equals 0, that's our resulting posterior after taking in one sample. And then we flip it again, we see a head. Now we've updated our distribution again. It looks like the first green one. And then we see 3 more tails and then 1 more head. And then ultimately, this is the current probability distribution that reflects our most up-to-date beliefs given the data that we've seen so far. So there's a lot of different criticisms between frequentist and Bayesian viewpoints of thinking about probability. So you could argue that Bayesian statistics is more subjective because you're making assumptions. You have to start with a prior probability. I guess it's cut off here, but if you guys have heard of Jeff Hinton or Jan LeCun et al., Jeff Hinton is famed for bringing neural networks back out of ignominy. And then Jan LeCun is most known for his work in coming up with convolutional neural networks. And I guess he's also famous because he has a meme page after him, convolutional deep memes or like convolutional teens or something like that. But he has some fun facts on that where there's this interchange. I don't think the Bayesian method is the best thing to do in all cases. Sorry, Radford, my prior probability for you saying this is 0, so I couldn't hear what you said. I don't know if this means that Jeff Hinton is a Bayesian or not, but I guess that's one way you can apply Bayesian statistics. But so some people criticize Bayesian statistics for being subjective, but arguably you could say that frequentist statistics is also subjective for reasons that I'll clarify a little more in the next few slides when we talk about hypothesis testing. So right now they're saying frequentist statistics, you have this element of subjectivity in the whole choice of the stopping rule when you're trying to apply hypothesis testing. Whereas with Bayesian statistics, you have subjectivity mainly in the choice of the prior. So let's turn to hypothesis testing, which is a crucial concept within statistics. Let's say you're a company, you're trying to determine whether or not this change was statistically significant, or whether or not a change you're trying to establish a statistical relationship between something, or you're trying to test a current hypothesis. So for example, let's say you flip a coin 1,000 times, and it shows up heads 300 times, and you want to know whether or not the coin is fair, then the approach that you take in hypothesis testing is to first come up with your null hypothesis, which in this case, the null hypothesis says that it's like the default hypothesis, the coin is fair. And then the alternative hypothesis in this case is that the coin is biased. We don't know what exactly what probability the heads comes up with exactly, but the alternative is that it's not fair. And then based on this, you would then compute the test statistic using what you actually observed and what you would have expected if the null hypothesis was true. And before you do all of this, you decide to work at some level of statistical significance. So say for p-value being less than 0.05 or being less than 0.1 or something. The smaller the p-value, the more statistically significant this is. So you determine the p-value based on the computed test statistic. And the p-value is really the probability of obtaining a value at least as extreme as what you've observed here. And then based on whether or not that p-value is smaller than the threshold, then you accept or reject the null hypothesis at some significance level. And this is widely used in the social sciences and the natural sciences, but it's really easy to apply wrongly. So actually there's a statistical study on this where scientists analyzed almost 800 articles and found that about half the time p-values were interpreted incorrectly, because it's not actually true to say that just because you failed to reject your null hypothesis doesn't mean that there's no relationship or there's nothing to be drawn from this. So actually this happened earlier on in this year, where scientists got together and they said there are a lot of problems with this method. It leads to, say, p-value hacking, where scientists put too much value and importance on trying to show statistical significance based on the p-value. And so you have p-value hacking, where you end up only reporting results where you manage to show statistical significance. And in general, there's just this problem of dichotomy, where we have this level of statistical significance we choose to be 0.05 to be meaningful. And then you're putting too much emphasis on deciding to follow through on the conclusions of a report based on whether or not you were able to reject or accept the null hypothesis. And this leads to, say, duplication of experiments or wrongly interpreted experiments, research, and then also problems with policy ensuing from that. So next I'll turn to statistical inference, which we can define as the process of estimating quantities of a general population based on a sample. So here we might be interested in point estimates, say estimates of the mean, or you might be interested in interval estimates or confidence intervals. So a confidence interval, which you'll probably encounter stat 231 or stat 241, say a 95% confidence interval, is also something that it's a little tricky to wrap your head around at first, or it's easy to misinterpret. But if we have a 95% confidence interval, it means that if we ran this test multiple times, then there's a 95% chance that our value of interest falls within that interval. But it doesn't necessarily mean that anything about our current interval. Like our current interval might not actually contain the quantity of interest. The 95% refers to if we ran this full approach several times, then that would be the probability that our interval captures our desired quantity. And then you can think of Bayesian statistics as this whole other shadow world where it has this analog to frequentist statistics. So here the analog might be credible intervals. And then with hypothesis testing, which is primarily when we talk about p-values, that primarily falls within frequentist statistics. But there's also a Bayesian approach if you run into Bayes factor. So that is like a similar flavor, but it's a different approach. So let's go more into Bayesian statistics. Again, we have Bayes' rule. We have the choice of prior. It's possible to choose uninformative priors to make fewer initial assumptions. And then an important concept that doesn't have so much to do with Bayesian statistics in theory, but it's important when actually applying these methods, is conjugate priors. So these are the choice of distribution for the priors based on the distribution of random variables, so that if when you compute the posterior falls into the same family of distributions as the prior. So this is important because it means that it makes our derivations and our calculations mathematically nice to work with. So let's say we're interested in estimating the parameter of a binomial model, then we should choose our distribution to come from a beta distribution or a beta family of distributions. And on the right, you can see some examples of beta distributions for different parameters of the beta distribution. In particular, there's the green line, which is just a uniform distribution, which is the beta distribution given parameters 1 and 1. So that would be, I would say, an example of an uninformed prior. There's conjugate priors, or there's pairs of probability distributions for other things that you might want to model. So if you're interested in multinomial distributions, then you can choose your prior from a Dirichlet multinomial, and then the posterior would also follow a Dirichlet probability distribution. There's also the gamma Poisson distribution, which is important for modeling, say, hospital stay length. Okay, so now let's turn to statistical modeling. So this is the science of fitting a model to your data. This falls within both data science and machine learning. Here it might involve feature engineering, for example, what features you think are relevant and contain salient information about what you really want to predict, for example, or feature selection. Maybe you have a lot of features and you want to find the most important ones. For example, Anzo talked about PCA, using that to reduce the dimensionality of your data set. It's also, I guess, related to feature selection. So here's an example from machine learning. Let's say we're conducting machine learning and we have a regression task where our data set is some x, where we have n samples, and each data point is a d-dimensional vector. And then we have labels y. So we have n labels y, one for each data point. It's a real value. Say we're trying to predict housing prices based on some features. So maybe the size of the house, maybe the number of rooms. Here are some examples of important statistical models. So linear regression, as you saw in the linear algebra talk, as well as logistic regression, which it's a misnomer because it's really a binary classification method, but it uses linear regression. There's also naive Bayes classification, latent Dirichlet allocation for natural language processing, which is just the natural language processing is just using computers to automatically understand human language. I think it's a bit jargony. So I'm not going to go too much into the math because it's already close to 8 p.m. and I'm sure you're all tired. But here's a fun case study that was actually turned into a Hollywood movie. So I don't know if you've heard of Moneyball, but back in 2002, there was this team called Oakland Athletics, and they managed to, on a low budget, win a historic 20 consecutive games. And they did so by identifying players who were undervalued, but would increase the chances of the team winning a game. And so their secret was data science in this case. And in particular, they used linear regression to analyze the data and come up with predictions. So on the right, you can see a little exploratory visualization of the different variables within, I guess the text is a little small, but there are different baseball terms like runs scored or runs allowed, and on-base percentage and slugging percentage. But here's the important part. Here's the mathematical model that we're working with. It's a linear predictor. So we have the beta i's, which are our parameters for our linear regression model. And then we have some random error, epsilon, which we usually assume to come from a Gaussian distribution with zero mean, but some unknown variance. And then we have the x's, which are our data points. And we're trying to determine, or all of this sums out to our response variable, or y. So here's what the data science team did, or here's what the associate general manager of the team did. They looked at historical data on how many wins a team had and whether or not they made it to the playoffs. And they determined that you probably needed at least 95 wins in order to secure your spot into the playoffs. And then working backwards from this, they fit a model based on the run difference and the number of wins to determine how many or what run difference they should probably aim for in order to secure 95 wins. And then based on that, run distance is just the difference between, I think it's the difference between runs scored and decreasing and runs allowed. I'm not a baseball fan, all I know is data science. But they looked at the factors that probably most increased the overall runs difference, and that was on-base percentage and slugging percentage. So based on that, they looked at players who would probably most help them in those metrics. And then they were able to, on a low budget, end up doing smashingly well in baseball. So here's a little tidbit about the math behind linear regression. You may have seen it from a least squares point of view, so not thinking about a probabilistic model at all, but instead trying to minimize the residual sum of squares. So here we have a loss function. We can think of this as an optimization problem. And actually a lot of machine learning tasks are phrased as optimization problems. So both optimization and statistics are key relevant fields to machine learning. But here we have a loss function, which is the sum of these squares, where our model is, here I'm using beta for the overall model parameters, which is typical in the literature. And I've appended a 1 to the beginning of the S vector because this is the same as having a bias term or having a, like when you have y equals mx plus b, it's like your intercept. So our model ends up being beta transpose s, or the dot product of those two vectors. And then we want to minimize this. But if we think about this also probabilistically, then we can think of having some Gaussian noise. And then what we want to do instead is we're interested in maximizing the likelihood of our data set given our model, based on our model parameters. So we're trying to find the parameters that maximize the likelihood of having seen this data. And these actually give the same solution for the model parameters, which might be interesting too. Except that we also have the variance of the noise in this case. Okay, so the last statistical modeling technique that I'll talk about is logistic regression, which is really a binary classification method. And it's built on a linear model. So we still have, let's say we only had beta 0 and beta 1, then our classifier would output 0 if the value was less than or equal to 0 and 1 otherwise. We can model this by using the sigmoid function. So the sigmoid function is featured on the right, but it gives 0.5 at 0, and then it tends to 1 as we move to infinity, and then it tends to 0 as we move to negative infinity. So if we compose our linear model with the sigmoid function, then we end up with some way of mapping the output of our linear model to a probability that lies within 0 and 1. So what the sigmoid function is doing is taking the output from the linear function and squeezing it between 0 and 1 in a way that nicely varies. And then at 0, it would be exactly 0.5. So here, these are our parameters, the same as what we had before. And what we would do in this case is, again, try to find the maximum likelihood estimator for our model parameters, and that we can do by, for example, gradient descent. Okay, and then the last thing that I'm just going to throw in is lasso, which is a statistical regularization and also variable selection technique. And it's just a fun tidbit. Actually, it was proposed by Rob Tibshirani, I think, who was a former Waterloo alum, who was a statistics and computer science major. But the idea is to impose an L1 norm penalty term to your overall loss function or your objective function. So what this does is it discourages you from overfitting. So because you have this cost for your coefficients being too large, and in particular, when you use the L1 norm as opposed to the L2 norm, which is ridge regression, then you end up with more sparsity in your model coefficients or in your model parameters. So you can think of it as well as a variable selection technique, because those variables whose coefficients are not 0 are the ones that are important in predicting your response variable. So here's a visual of why some of the intuition between why L1 imposes sparsity, whereas L2 regularization doesn't so much. you can see that LT regularization, it has a higher penalty for terms that are large. And so you end up targeting the large terms instead of the smaller terms, whereas L1 regularization does not do that. So that's all that I'm going to talk about for today. If you're interested in learning even more, there are some textbooks which I recommend. All Statistics is available free online. And I find it a lot less dry than ESLII. But the last two are both in our office, and you're welcome to check them out. There's also some links for reading if you're interested at all. And you can always follow up in the Discord chat. So thanks so much.
Okay, well, thank you everyone for being here with us for like nearly 2 hours. So I would like to thank Anzo and Frieda for taking the time to come here and bless us with their infinite knowledge. So yeah, if you have any feedback, comment you'd like to share, feel free to just say on the Discord. If you have any idea for workshop that you that too. So yeah, so we are on the lookout. We'll be announcing more as well. So have a good night, everyone. Travel home safe. Enjoy the rest of the evening.
I forgot to ask the
Thank you.
TensorFlow.
You know, it doesn't deny it actually.
Okay.
I'm gonna say it here right now next
No,
week.
it's okay.
Yeah, I think there will be.